Webinar and meeting sponsored by the CTS Transportation Safety and Mobility Research Council. My name is Tony Fisher. I'm a transportation planner at the Met Council, and I serve as the chair for this group. So a little background on the research councils. The CTS councils provide a forum for transportation professionals and researchers to exchange information on current transportation issues and trends. They bring together university faculty and staff with practitioners from the public and private sectors to recommend direction and participate in improving the center's research, education, and engagement programs. Today's webinar will feature presentations on addressing challenges for autonomous vehicles on winter roads and risks of stealthy cyber attacks on connected and automated vehicles. I'll share more in a moment, but first I'd like to turn it over to our Council Vice Chair, Joe Gustafson, who is co-facilitating this webinar. Joe?
Good afternoon, everyone. As Tony said, I'm Joe Gustafson. I'm the traffic engineer for Washington County Public Works and this year's co-chair for the Transportation Safety and Mobility Council. Thank you all for attending today's webinar. So I will just slide into the housekeeping items here. We're looking forward to audience participation and questions today. We encourage you to use the raise hand feature or type the word share in chat if you have a question or comment. Then the host can unmute you and you can share your question verbally. Or if you prefer, you can use the Q&A at the bottom of your screen to type your question or comment for the speakers. There will be audience Q&A following the presentation. We do also have some professional credits available for this meeting. I want to let you know that this meets the continuing education requirements for 1.5 professional development hours for us engineers, and 1.5 American Institute of Certified Planners, AICP, certification maintenance credits. If you need a PDH form for this event, please send a chat message to all panelists with your name and email, and we will email you a form following today's events. So I will, with that, turn it back over to Tony.
Thanks, Joe. And then let me just share that we have the benefit of the fantastic staff from CTS. We have Gina, Baas, and Sam Han-Dulville from CTS helping us with this webinar. And so the webinar will feature presentations on connected and automated vehicles from two contributors to the CTS Future Mobility Series. We have Rajesh Rajamani and Raphael Stern. You'll also hear updates on CAV-related research at the U of M's MnCAV ecosystem from CTS Associate Director Gina Baas, and learn about the latest CAV activities at MnDOT's Connected and Automated Vehicles Office from Thomas Johnson-Kaiser. I'm pleased to welcome today's speakers, Professor of Mechanical Engineering Rajesh Rajamani, Raphael Stern, Assistant Professor of Civil Engineering and Environmental and Geoengineering, Thomas Johnson-Kaiser, MnDOT's Connected and Automated Vehicle Office, and Gina Baas from the Center for Transportation Studies. Thomas?
All right, well, thank you everyone for having us here today. I'm really excited to just share some updates on what we're doing in our Connected and Automated Vehicle Office at MnDOT. So as we see that connected automated vehicles are really going to be an important part of our future of transportation. So at MnDOT, we're looking to plan and prepare for how this technology could potentially impact Minnesotans. Before I get too far into things, just want to quickly define what we mean when we say connected and automated vehicles. So there's two pieces to that. The connected side, which are vehicles that use technology to communicate with each other, connect with traffic signals, signs, or other road items, or could obtain data from the cloud. Then you have the automated side, often known as self-driving. These automated vehicles use technology to perform some of those driving tasks like steering, accelerating, braking with little to no human input. So today I'm just going to highlight a few of our projects we have going on at MnDOT, just at a really high level. I'm happy to take questions, or if people want more information on these projects, feel free to reach out to me or anyone in our Connected Automated Vehicle Office at any time. We're always happy to chat and share what we're up to. The first project I'll share about is one of our shuttle demonstration projects we have going on. This is called Bear Tracks. It's taking place in White Bear Lake, so just a suburb outside of the Twin Cities here. So this is a 12-month pilot project that's testing technology in White Bear Lake. It started in the summer of 2022, so it'll wrap up this coming summer. It was funded what's through our CAV Challenge program, which is a competitive grant program that is kind of rolling RFP for anyone to apply for funding to test out this technology. And this is actually one of 3 pilot projects we have or had in the state. Our first one was in downtown Rochester, the Med City Mover, that wrapped up last summer in 2022. Then we have this Bear Tracks project, which is taking place in a suburban environment. And then I'll also highlight our Go Marty project, which is taking place in a rural environment in Grand Rapids, Minnesota. So a little bit about the shuttle in this project. The technology we're using is a highly automated shuttle that's provided by a company called Navia. You can see in the upper right-hand corner there, can hold up to 11 passengers. It's a 100% electric vehicle. This is a slow-moving shuttle, so it travels about 10 to 12 miles an hour. It is on the road with other vehicles. You'll see the route shortly here. It is equipped with a ADA compliant ramp, and this shuttle and all of our shuttle projects that we have a vehicle attendant on board at all times to take over as necessary and assist passengers. So this is about a 1.5 mile route in White Bear Lake. It has 4 stops you can see on the route here, taking folks from local senior living facilities or adult day centers for folks with disabilities to the local YMCA. So it's a 1.5 mile route with those 4 stops, and it operates 5 days a week, kind of in the middle of the day time frame there to avoid any of the peak traffic hours, since it is, as I mentioned, a slow moving shuttle at that 10 to 12 miles an hour. So I'm just quickly go through these projects. So next I'll get into our Go Marty project. So as I mentioned before, this is another autonomous shuttle project we have. This is taking place in Grand Rapids, Minnesota. So this one is an 18-month project. We launched in early October of 2022, so it'll run through March of 2024. Unlike the White Bear Lake project, which just has 1 shuttle, Go Marty has 5 vehicles that operate in about a 16.5 square mile area. So this is quite a bit different project where these shuttles are on demand and point to point. So the shuttles can be requested through either a May Mobility app that people can use on a smartphone, or by calling into the local call center, First Call 211. So there are about 70 pickup and drop off points within that 16.5 square mile area. So when folks request a ride, it will tell you where the closest pickup or drop off point is, say where you want to go, and it'll drop you off at that closest point. Our technology provider on this project is May Mobility. These vehicles are also quite different. They're actually Toyota Sienna minivans that have a number of equipment and technology on them. And 3 of those vehicles are wheelchair accessible. You can see in the image here on the left. So really happy to provide that additional transportation options for folks. As I mentioned, we do always have an autonomous vehicle operator on board that's always engaged. These rides are free during this 18-month pilot. We operate 6 days a week, Tuesday through Sunday. And this is really exciting project because it's one of the first rural and large scale deployments of autonomous shuttle in the country. So really excited to be learning a lot about how these technology operates in a rural environment. A little bit quick stats for the project to let you know how it's going so far. So through March, we have we've had about 1,750 riders, and about 15% of those, so a little over 260 of those, have been wheelchair accessible rides. We're seeing a high percentage of those repeat riders, so about 85% of our riders are repeat riders, so people are utilizing these vehicles and this demonstration continuously. And we've driven over 46,000 miles throughout about the first 6 months of the project. So shifting gears a little bit, I want to highlight another project we have that's more on the maintenance side of things. So seeing the different flavor that this technology can be used. So this project is called our Automated Truck or Trailer Mounted Attenuator, or ATMA. So a little bit of background for those of you who might not be familiar. Truck mounted attenuators, this is a device that's used in work zones that's attached to or towed by a truck. The purpose of it is to absorb the energy from any potential crash. So it's placed to protect that work crew. So with how these work is there's a pair of trucks, there's a leader and then a follower that's following the exact path of that leader truck. What our goals for this project is the leader truck is driven manually, where the follow truck will be driven automatically. And we'll get into a little bit more of that soon here. And the objective long term is to remove those operators from that second follower truck. Currently, we aren't quite there yet, and we do have a operator in that truck while we're testing, but that is the ultimate goal we're testing out for this project, is to be able to increase that safety and remove that worker from harm. So here's an image of how this works. So we have that leader vehicle that drops these wireless e-crumbs that the follower vehicle, the automated truck mounted attenuator, will then follow. So it follows the exact same path. For those of you interested, a little bit more images or details in some of the technology specifically, but won't get into that level of detail today. So what we've done so far, this has been a multi-year effort. So we've had these trucks, which are provided by Kratos, we've had them outfitted for the ATMA system. We've done some testing on a closed track at Elko Speedway. We had some folks from the Metro Lakeville shop at MnDOT perform this ATMA operation, attempting to kind of integrate into their existing work as some extra work. This was happening last summer. We learned a lot. Some significant challenges occurred in the metro area. Some system failures that required the truck to be out of position to restart. A few other challenges with dashboard warnings and visibility, and just that limited hours of testing be performed, with the cause being that extra work on top of what the already Lakeville shop staff was doing. So we're taking a little bit of a different approach this coming summer. We made a lot of improvements, software improvements and hardware improvements to improve the system. And then we're hiring our CAV-X group is hiring 2 temporary positions to operate the ATMA system throughout the entire summer. So they're going to be testing it throughout all the MnDOT districts with district crews this summer. So it's going to be an opportunity to test this in different situations and throughout the whole state, and for these crews throughout the district to see the ATMA system in person and interact with it. The last project I'll highlight quickly here is an exciting project we just got going in February called Community Driven CAV. So the goal behind this project is that we envision a project or a future where the community is at the forefront of planning and implementing new technology such as CAV. So traditionally, CAV technologies are often developed by companies or universities and then kind of tested in communities. So it's really that they develop a technology and looking for a community or a problem that technology may solve. So instead, we kind of want to split the script there, and we want the community to help identify what technology or uses of technology Minnesota plans for that could help address their issues. So we're going to do 4 main things with this project. First, we're going to host a number of community listening sessions. So we're partnering with an organization called Creative Enterprise Zone, which some of you may be familiar with. It's very close to right in between the Minneapolis and St. Paul campuses for the University of Minnesota. just north of I-94 and east of 280, so right in that St. Paul, Minneapolis border there. So we're going to host a number of community listening sessions to help identify the community's vision around three main topics: businesses and jobs, social services, and live, work, and play. And then we're going to bring together some community members along with some technical experts to have some workshops to brainstorm about the future of transportation through some creative facilitation. From there, we're going to create two deliverables. So one is a community-driven CAV demonstration action plan. So this will kind of summarize what potential use cases CAV might have from the brainstorming and listening sessions to help address some of those challenges that the community is facing. And then lastly, a community-driven planning framework. So the idea behind this is that other communities could take this effort and utilize this framework to go about a similar process. So this will kind of summarize that approach, lessons learned, and be a resource for other communities to lead similar planning effort. So that was a very quick overview of some of our exciting projects we're working on at MnDOT in our CAV group. I'm happy to take any questions.
Thanks, Thomas. It's great to see the energy and effort that MnDOT's putting into this important topic. Yeah, if anybody has questions or comments, please feel free to put them in the Q&A, put them in the chat, or raise your hand. But otherwise, I'll start off with one question. I think we've long heard about maybe the need for some roadway improvements to support automated vehicles, and thinking especially about striping, edgeline striping. Is that kind of what you're seeing? Are you seeing other things that you wish were in the ground as you do some of these testing?
Yeah, with some of these projects, striping is still an important factor for a lot of this technology that we're seeing, but not necessarily. We are seeing some good improvements in winter weather where we're not able to see striping that well. We're improving the amount of time that these vehicles can be operated autonomously. So I would say it's still undetermined, and the technology is changing so quickly, and there's so many different technology providers out there. There's not clear guidelines that say you need to do X, Y, Z for autonomous vehicles to operate. So I think the key is to just be continuing to learn about this technology, to be doing this testing to better understand what may be done, and anything as our approach at MnDOT, anything that we do should benefit not only human drivers, but if it's benefiting drivers autonomously, should also be benefiting human drivers as well. So wanting to make sure that we're keeping both in mind there, since we know there's going to be for a long time, and all of our lifetimes, it'll be a mixed fleet as this autonomous technology continues to evolve and be more integrated.
Great. I've got a question in the chat for you. Can you clarify the number of unique riders for the Go Marty pilot? You mentioned that 80% were repeat and total rides, I think, but how many unique individuals are using it for rides?
Yeah, that's a great question. So I don't have the exact number on that because so when you request a ride, it's just the person that requests the ride that we can have document their information. So maybe you requested a ride one time and then you rode with someone else a different time. So we don't have the exact number, but I would say we've seen probably about 300 or so unique riders with that high level of, with that 1750 or so total riders and that high 80-85% of repeat riders. So it's around that 300 unique riders.
Great. And Thomas does need to leave before 3 o'clock for another engagement, but so this is your chance to ask any questions. I was wondering about that shuttle in White Bear, I think it was, that crossed White Bear Avenue. And if you saw any special challenges there, given how busy that street is, maybe how wide the crossing distance is.
Yeah, so I don't think we've seen any particular challenges there with that crossing, but we did work with the city and are working with some connecting technology on the signal there. So did implement a roadside unit to help with that. So with any of our, and along with our Med City Mover project that we had in Rochester, any of the signals that the shuttles are interacting with did take some additional work to get that program. So that has helped, but we haven't seen any specific challenges with that intersection there.
Okay, we've got just a couple more minutes if anybody's got a question, but otherwise my last question is going to be, when are we going to get level 4 and 5 out there? What's that going to look like and when?
Yeah, so two of these projects, so the White Bear Lake shuttle and the Go Marty shuttle are level 4 vehicles. So they are, out there in kind of that testing mode, research and demonstration today. So continuing to see what the specific use cases and scenarios this technology continue to be used. And also we're wanting to hear from the community that are experiencing this technology, what they may think of this technology and what they may think it would be best used for to help solve their transportation challenges. So I could see level 4 continuing to grow slowly here as use cases and more testing is done. I was just down actually in Phoenix this past weekend and took a completely self-driving, no driver in the vehicle, Waymo vehicle around town a little bit. So that was on the road offering rides for folks. So some of this technology is there. There are challenges, as we know, with Minnesota and our winter weather and other weather instances that they see less so in other areas where they're testing this technology and utilizing it more. So I could see level 4 continue to expand, but level 5, I think it's going to be a very, very long time until we see fully autonomous in all circumstances, all situations type vehicles that level 5 would be. So haven't reached that yet, and I think we're still quite a ways away from level 5.
Okay, Joe can correct me if I'm wrong, but I think there's just one last question in the chat. And that's about if you've been collaborating with anyone from Wisconsin. I guess I'd broaden that out to, other Midwest states. I'm sure you're connected to national level work, but where are you working with in the Midwest?
Yeah, so we're part of a lot of national and local organizations, NASTO and ASTO and a lot of those different, and some pooled funds and a lot of different organizations. So yeah, we definitely are connected with our partners in our other DOTs, meet regularly with those folks to see what they're working on and always open to continue talking. We haven't collaborated on a specific project necessarily with DOTs. Well, actually our ATMA project is part of a pooled fund nationally. We're working with some other DOTs that are doing similar ATMA work, but yeah, so haven't have a specific project with our fellow DOTs in the region, but always in kind of communication and sharing lessons learned from our various projects that we each individually have.
Thank you, Thomas. Thanks for being with us today. A virtual round of applause.
Yeah, thanks everyone, and as always, feel free to reach out at any time with any further questions.
Great, thanks again. And now we have Dr. Rajamani up next.
Thank you, Tony. Can you see my screen?
Looks good.
Okay. I'm going to talk about special challenges for autonomous vehicles on winter roads. And this is a quick outline of my talk. I'll give you a initial overview of autonomous vehicles in general and the MnCAV vehicle in particular, and tell you a little bit about some of our work on the MnCAV vehicle. Then I'll talk about the challenges for winter operation and talk about some potential solutions to these challenges. So the two core elements of autonomy are basically adaptive cruise control and steering control. So in the case of adaptive cruise control, as all of you probably know, it's an extension of cruise control where the car has a radar and it's able to measure distances to other cars. And what the system does is it operates at a desired speed set by the driver. And so the throttle and brakes are automatically controlled. But if there is a slower moving car in the same lane, then the car basically it switches from speed control to spacing control, and it maintains a distance behind the car that it is following. Typically, this distance is a time gap. So, for example, the time gap might be 1 second or 2 seconds. And so these ACC systems were introduced in the market in the US in 2000. And many brands now offer at least some version of ACC. So even low-cost cars like the Toyota Corolla offer ACC. But typically, most of these systems operate only at highway speeds, so at speeds greater than 40 miles per hour. Okay, can you still hear me?
You cut out for a moment.
Are you able to hear me?
Yeah, a little bit. I don't know how good the
Okay,
sound
okay.
quality
So
is.
hang on 1 second.
That sounded much better.
Sorry about that.
Oh, that's sounding much better now.
Okay, so the other element of autonomy is basically automatic steering. So in the case of automatic steering, all the cars sold on the road use cameras to measure distances to the lane boundaries. So using cameras, you measure the lateral distance to the lane boundaries, find your distance from the center of the lane, and then this distance is used as the feedback control for automatically controlling steering. So, the types of systems available on cars sold in the market are warning systems that warn you if your car is going to leave the lane. And then there are also automatic lane keeping systems that basically entirely automate steering control. So they take care of steering and enable staying in the lane, following the lane. So these two elements, adaptive cruise control and automatic steering, those are the two basic elements of autonomy. And these are available on level 2 cars. So they're available on many cars sold in the market. So in the case of level 2 cars, the driver is responsible for the safety of the car. So oftentimes you need to have your hands on the steering wheel, and you are responsible for finding out if the system is operating safely, and you have to take over if the system is not able to really operate by itself. So what do we have beyond ACC and automatic steering? Here are some systems that are available in the market. So we have the Cadillac Super Cruise system. So this is a system that is available on a few map regions. So for example, in the Twin Cities, it includes 35E, 35W, and 494. And here what the system has is an adaptive, in addition to adaptive cruise control and lane centering, it has a few other features. It doesn't require the driver to have hands on the wheel. You still cannot, turn back and speak to somebody in the back seat or do things like that. There is a camera that is monitoring you and ensuring that you're looking at the road, but otherwise it doesn't require you to have your hands on the steering. It does automatic lane changes. You still have to request a lane change, but it will do automatic lane changes. It uses LiDAR maps. And so in addition to looking at the lane boundaries, it has other position measurement technologies. And so it's able to do more reliable steering control. So another system that goes beyond level 2 is the Tesla Autopilot. So the standard Tesla Autopilot is available on all Teslas, and that is essentially an ACC plus automatic steering system that works in stop and go traffic. But you can pay an extra $10,000 and you can get a beta option on a full self-driving system. And so what this full self-driving system does is it contains more autonomous driving features like automatic lane changes, navigate on autopilot. So it will basically make automatic lane changes. You don't have to request the lane change. It will make those lane changes by itself. It will also take exits when needed, change between highways, for example. It also recognizes traffic lights and stop signs, and so it can operate on local roads in addition to highways. So it's got quite a few features beyond the basic autopilot that's available on all the Teslas. But on this system as well, the driver is required to have hands on the steering wheel and be prepared to take over at any time. So then the MnCAV vehicle that we have at the University of Minnesota. So this is a level 2 system. So the Center for Transportation Studies owns this vehicle, and so they raised the money for it. What it is a Chrysler Pacifica minivan. This was instrumented by a company called DataSpeed. So they implemented the by-wire interfaces on this vehicle and the firmware and software. Are you still able to hear me?
You cut out just for a moment.
It's okay now?
Yes.
Okay. So the MnCAV vehicle essentially has steering control. And so this is a level 2 system for operation on freeways. It has automatic steering control. It uses a Mobileye camera, which is a commercially available system, uses lane markings to again find the distance from the center of the lane and to do steering control. It also does lane changes on demand, so you can ask for a lane change. It uses LiDAR segmentation to decide if it is safe to do a lane change, and then does the lane change when it is safe to do so. So it also has adaptive cruise control. And so adaptive cruise control, like we talked about, includes speed control and spacing control. But this was really designed for mostly highway speed operation. So some of the recent research work that we did, I'm going to talk about that on the next slide. So we are doing some work on improving the performance of the automation on the MnCAV vehicle. So as far as the adaptive cruise control system, one of the problems with the ACC system that came with the MnCAV vehicle was it did not operate when the speeds drop. Also, it had jerky operation, especially when when you use larger time gaps and when other vehicles cut in, the operation was quite jerky. So what we did is we implemented smoother ACC operation that included transitional maneuvers. So basically, with the transitional maneuvers, we are able to smoothly switch between speed control and spacing control. And if the lead car makes a lane change and goes away, or if some other car cuts in, those operations have become really smooth, and you don't notice any hard braking. So those things work out very nicely now. We also have stop and go operation under heavy traffic. So that works nicely now. So some of the challenges that we had for stop and go operation was that the radar system was designed to discard stationary objects. So stationary objects were not tracked, but when you have stop and go traffic, there are cars become stationary objects when you have stop and go traffic, and so then it really becomes a problem about how you can have automated operation under stop and go. And so what we did is we incorporated the use of LiDAR for stop and go operation, and so by combining radar and LiDAR, we've been able to get stop and go operation. We also did smoothed profiles for complete stop and restart. So in addition to just using radar or LiDAR for feedback, we also have some additional open loop profiles that we implement when the vehicle is almost at a stop and when it is just starting from a stop. So all of these things have helped make the system work well. What I'm going to show you now is a quick video of the MnCAV vehicle under heavy traffic. So what you can see in this video is, both automatic steering control and ACC. You can see the set speed set by the user and the actual speed. So the actual speed is lower because of the traffic on the highway. So the car is supposed to go.
I think we lost Raj for a moment. Hopefully for just a moment. See if we can get him back.
I'm guessing the video may have stretched his bandwidth too much, so it might have kicked him out.
Yeah, I wonder, Gina, do we want to jump into Raphael's presentation right away? I don't know how long it's going to take to get Raj back.
I'm ready to go now, if you want me to go now, and then we can finish let Raj finish his talk once I'm done. If that, I don't want to interrupt Raj like that, but if he's not here right now.
Yeah, why don't we go ahead?
Okay, apologies to Raj, but I'm going to share my screen. Can you see my screen right now?
Yes.
Great. And you see the correct one, right?
Yes.
Okay, great. So should I just go ahead and start now?
I think so, yes. Let's do it.
Great. So my name is Raphael Stern. I'm an assistant professor in the Department of Civil, Environmental, and Geoengineering here at the University of Minnesota. Just a few feet away, just a few hundred feet away from Raj. My internet seems to be doing okay though, so I'm gonna see. Hope this doesn't fail on me. I'm gonna be talking today about something that I've kind of recently gotten really, I don't want to say worried about, but certainly interested in and intellectually concerned about to some extent. And it's something that I was able to sort of put a good deal of thought into over the last year or so. Both sort of through a seed grant from CTS, so thank you, and then also through this Future of Mobility initiative through CTS. And so what I want to talk about is this topic of risks of stealthy cyber attacks on connected and automated vehicles. And the lens that I'm looking at this through is very much from, I'm a civil engineer, I'm a transportation engineer. I think about traffic flow, and I'm really going to think about it from that sort of traffic flow perspective. Think about it in terms of like, what do potential cyber attacks look like, and what do they mean for traffic operations? And that's really the lens that I'm trying to think about this through. Raj did a really nice job of sort of summarizing the state of practice in terms of automation right now. And I think this is sort of looking at, well, what happens when people try to tamper with that? I don't think I really need to say this, but cyber attacks are something that are becoming more and more persistent. We've seen a number of high-profile cyber attacks that have taken down large pieces of infrastructure, and there's a tremendous cost to these. And with a sort of increasingly digitized world, I think there's increasing number of what they call attack surfaces. So just opportunities, avenues for attack, places where you can compromise and cause potentially major disruptions. And so what I want to look at is really sort of automotive world, and specifically look at the types of attacks that might occur on the individual vehicle, and then try to translate what those then imply at the level of the level of traffic flow and transportation management, and what these might look like. And so to motivate this, I want to share a slide that I oftentimes share with my undergraduate students to just kind of demonstrate sort of how ubiquitous computation is. So when you look at the original Unix software, you have about 10,000 lines of code. So if you think about sort of how much text is there to make that software run, about 10,000 lines of code. If you look at an iPhone app, it's about 40,000 lines of code. Lines of code is roughly a proxy for complexity, and sort of how much this thing depends on computation. The space shuttle had about 400,000 lines of code, so about a 10-fold increase from an iPhone app, which is kind of impressive that they flew things into space and back with really just like, fewer apps than I have on my home screen effectively in terms of computational ability. Windows 3.1, the original Windows, about 2 million lines of code. HD DVD player, perhaps somewhat dated, but about 4.5 million lines of code. World of Warcraft, all of it is only about 5 million lines of code. A browser is about 10 million. And I think it's kind of surprising what types of things here are just much more complex than other things that we kind of take for granted. So the entire Android OS, a fighter jet is about 25 million lines of code. Windows 7 is about 40 million lines of code. Facebook about 60. And a modern car, not an autonomous or a connected and autonomous vehicle, but just a modern car alone has about 100,000 lines of code. So before we think about sort of automation, connectivity, all of that, just the cars that are on the road today are already basically cars with computers with wheels, right? They're already so much more complex, computationally speaking, than anything that we've sort of seen before. And this obviously brings us sort of to a lot of different opportunities for malicious actors to compromise this. I want to focus on 3 primary types of attacks that I focused on in my Future of Mobility piece that I think are particularly relevant when we talk about sort of CAVs and cyber attacks. So the 3 types of attacks that I want us to be thinking about today are infrastructure-based attacks, communication-based attacks, and sensor-based attacks. And we'll go through some examples of these in just a few minutes, and then talk about what they potentially could look like when it comes to sort of transportation management and what the impacts might be for transportation. So infrastructure-based attacks, this is basically you compromise some sort of physical infrastructure at the roadway level. So this might be, for example, you tamper with some sort of roadside units. For example, one thing that's become quite popular is this idea of you have signal phasing and timing being shared from the traffic signals to the vehicles to allow the vehicles to adjust their driving and operate more efficiently. And you can imagine that if you somehow compromise that roadside unit, you could be sending improper signal phasing and timing to the vehicle. And in the best case, this might just mean suboptimal performance. The vehicle doesn't actually know what the true signal phasing and timing is and performs suboptimally, maybe increases fuel consumption. But in the worst case, could increase crashes, right? You could cause crashes by conveying the wrong SPAT messages. Communication-based attacks, they might look similar because in theory, this is communicated information that's being tampered with. But communication-based attacks, you're kind of actually the idea is that you're actually tampering with the communications, and maybe sort of a malicious, often called man-in-the-middle attack. Some malicious actor is kind of taking in that information and then actually broadcasting a slightly different signal that makes this CAV here think that the CAV in front of it is telling it something different. And this could again sort of be catastrophic. These could be basic safety messages that you're tampering with, or this could be just a minor inconvenience. This could be, some sort of message about intentions of what the CAV wants to do that then this following CAV misinterprets. And sensor-based attacks. So sensor-based attacks live entirely on the vehicle. They don't necessarily require connectivity. And in sensor-based attacks, you change the things that are going on the vehicle itself. And perhaps maybe lead this vehicle to think that there's no car in front of it, or that the car in front of it is much further away, which you can imagine would lead to all sorts of safety considerations, right? So if this vehicle doesn't see the vehicle in front of it because the radar that it's using to see that vehicle in front of it is being tampered with, you can imagine that could be pretty detrimental. Okay, so in terms of what do these actually look like, I want to look at two examples that are somewhat famous, but I think really nicely illustrate what this potentially could look like. So the first example is the top. I think of this as an infrastructure-based attack. And the infrastructure-based attack example that I gave a minute ago of a roadside unit being compromised, that might actually be a pretty complicated attack where you have to do a lot of sort of tampering with actual physical hardware. And you might think, well, somebody's going to certainly notice that and report it. But it turns out that these infrastructure-based attacks can actually be quite simplistic and yet quite effective. So what's going on here pictorially? Well, it turns out that a lot of vehicles, as Raj was just saying as well, use all sorts of different sensors, including cameras, to sense the environment around them. And so a typical connected automated vehicle might use the camera to observe sort of what kind of signage is around it, and then take that to interpret the local context and make decisions, right? Decide to stop at the stop sign because that's what it's being told to do. However, if you know the code that is used, it basically ends up being a bunch of neural networks. So basically ChatGPT, but for cars, that is used to determine what is out there, what does this picture correspond to, what's in each of these pictures. If you know that code, you can adjust signs very carefully to make them look completely different to the vehicle. So this is work that was done by someone named Bo Lee at the University of Illinois, who just a couple of years ago showed that basically if you know what kind of software this car is using, you can maliciously just place stickers on a stop sign, and what the car sees in this case, so this is just a stop sign with a couple of stickers placed in very strategic locations. You feed that through the neural network that car is using to interpret the images around it. And what you see, or what the car sees or thinks it sees, is a speed limit 45 miles per hour sign. And you can imagine how, from a safety perspective, this has really big implications. And this is not a very sophisticated hack in terms of what you're doing. You're just putting stickers on infrastructure and potentially making the cars think the environment around them looks very different. Now, of course, this is a very carefully chosen example, but it sort of shows how if you know what the data this vehicle, or what the models are that this vehicle is using, you can really potentially do some pretty serious damage. The other one is sort of a communication-based attack and a sensor-based attack, sort of 2 in 1. This is a really famous example by these two hackers who, this was featured prominently in Wired magazine and a whole bunch of other places. These two hackers basically took a Jeep and figured out how to hack into the Jeep from remotely using communications that the Jeep was making with the cloud through telematics. And then they were able to turn off the engine, turn on the hazards. Okay, turning on the hazards, maybe not that big of a deal. Turn off the engine on the highway, pretty big deal. Or in this case, actually just steer the Jeep off the road and into a ditch. How did they do this? Well, it turns out that they hacked into it via the infotainment system. And the infotainment system was linked up with the basic CAN, or the basic messages being sent on the car. And by doing that, they were able to relatively easily get into the actual sort of onboard communications on the car and do pretty obvious substantial damage. Okay, so this is sort of maybe motivates why I think these attacks, computation is everywhere when it comes to vehicles. Not just CAVs, but particularly CAVs are, they are basically primarily computers that happen to have wheels. And there's already a bunch of examples of both infrastructure-based attacks and sensor-based attacks that show that, this is certainly possible. Okay, so I started with the stealthy attacks, and I want to explain what I actually mean by that. Because what are stealthy transportation attacks? So the attack that was showed here in Wired magazine, where they took a Jeep and drove it off the side of the road, I would argue that that's a relatively obvious attack. Now, is it a good attack? No. Obviously, there's serious safety implications for cars suddenly stopping or suddenly driving off the road. But if all of a sudden a large part of cars or number of cars or all the cars from a certain manufacturer that got some malicious software update start driving off the road, it's going to be pretty obvious what happened. And it's going to be maybe not easy to fix, but certainly easy to, to have some sort of recall that says we need to get all these cars off the road right away. But stealthy attacks are a little different, right? So stealthy attacks are attacks where you imagine you just change that driving behavior. Instead of driving it off the road, you just have it drive a little bit differently. And that slightly different driving could potentially cause widespread disruption. So you might not actually notice anything on the individual vehicle that's been compromised. But if you're an infrastructure manager, you might notice that your capacities come down by a couple of %. And so I want to motivate this with some work that I've been thinking about for a long time, which is sort of understanding how traffic jams form and what causes traffic jams. So if you've seen me talk before, you might have seen me talk about these here, because I think these are really important. These are traffic jams. And it turns out that, we see them in the wild. We can reproduce them in the lab. The way cars drive causes traffic jams. And for a long time, there's been a lot of sort of promise that automated vehicles, by driving differently, even if we don't have all of the vehicles automated, even just a small number of automated vehicles potentially have the opportunity or provide the opportunity to change the way this happens and to change that traffic flow. And I've done a lot of work on this. It turns out that with just one vehicle out of 20, or so like 5% of vehicles driving a little bit differently, you start to see substantial difference. I want to show one experiment that I did a couple of years ago that shows this really nicely. And you'll see where I'm going here with this in just a minute. So the vehicle with the arrow on top of it, that's an automated, autonomous capable vehicle. All the other vehicles are human drivers. And what happens is, relatively quickly, they're all driving, that automated capable vehicle also has a human driver in it right now. Relatively quickly, traffic jams emerge. And that's kind of inevitable. But what you can do if you turn on the automated vehicle's self-driving capabilities and control it just right, so that's what we see with the red arrow, it's able to smooth out that traffic. And the really big take-home message here, the thing that I really want people to see here is, yes, automated vehicles have the potential to change traffic and improve traffic. And the way they potentially will do that is by basically changing the emergent properties of that flow. And so the important thing here is that even if we only have a small number of automated vehicles driving differently, they can make huge improvements. In this case, we saw an increase in throughput and a decrease in fuel consumption of all vehicles. But I want you to think about that in the other way. Imagine that a vehicle is just driving, so that vehicle was just driving a little bit better, and that greatly improved traffic flow. What if that vehicle were driving a little bit worse? Many of you have probably experienced this. Oftentimes, it just takes one bad driver on the road who's swerving a lot, or possibly changing lanes a lot, or just not driving consistently to deteriorate the entire flow. And so you can imagine that if you compromise just a couple of vehicles in that flow, and you get them to drive just a little bit worse, not a lot worse, just a little bit worse, that potentially, under the right circumstances, could be really detrimental to the flow. And these big improvements in fuel consumption that we see from autonomous vehicles potentially improving flow could lead to big increases in fuel consumption if the autonomous vehicles are compromised and actively deteriorating the flow. And I want to sort of point out to Raj's point earlier, there's a spectrum of autonomy, right? And so if you think about no automation, that's what we might, that's what most people think of as cars. But really, there's a lot of different levels of autonomy. And in each of these levels of autonomy, we're basically taking more of that control and handing it over from the human driver to the vehicle. And so, what Thomas was showing earlier was, level 4 automation on the roads. But I would argue that a lot of this could also be possible at levels 1, 2, and 3. And so if you start to think about, vehicles being compromised, vehicles driving just a little bit worse, and that deteriorating the flow, that could actually start happening even sooner if we're not careful. So I've been thinking about this for a while, and I've been sort of experimenting with this a little bit to see what happens. And so I wanted to show a simulation that I ran that kind of gives you a sense of what's going on. So these are space-time diagrams. If you're a traffic engineer, you've probably seen these before. Basically, on the horizontal axis, we've got time. On the vertical axis, we've got position along a roadway. And each line represents a vehicle. And the green vehicles are human drivers. The red vehicles are compromised automated CAVs. And the blue vehicles are non-compromised CAVs, right? So this is the setup that we have up here. And under normal conditions, you see traffic is quite smooth. You see a couple of waves emerge, but relatively smooth driving. Now, what we've done over here on the right is we've just changed the driving behavior of the compromised CAVs just a little bit. We basically just injected a tiny bit of noise, a little bit of extra bad driving. Not a lot worse, not bad enough that if you were in that car, you'd notice it driving poorly, but it's just driving a little worse. And what you see at the level of the flow is you see this massive traffic jam that starts to emerge. And if you were to run this longer, I would imagine that this traffic jam gets worse and worse as it propagates. And so this is sort of the potential at the infrastructure level for these to really cause some pretty significant damage. Okay, so as the next question is, what do we do with that, right? How can we detect this? Because the whole point of these stealthy attacks is that they're stealthy, that they're difficult to detect. If you're the individual driver in a vehicle, you're not going to notice that your vehicle's driving any different because it's not crashing into other cars. But you might see an increase in fuel consumption if you're or a decrease in throughput if you're an infrastructure manager, or sort of a long-term average increase in crashes. And so one way to think about this is to basically harness that same artificial intelligence in reverse. And so what we see on the left, this is sort of some work that I've been thinking about recently. These look like cats. They're not actually cats. They've built neural networks, generative adversarial networks that create things that look like cats. And so these models are models that are very good at creating things that look real. This is exactly what ChatGPT is. It's a generative adversarial network that creates things that look real. And imagine you could use it in reverse. Basically ask it, does this look real? And that's exactly the idea that I'm trying to pursue here. So basically, can we look at traffic flow? Can we look at trajectories, feed it backwards through something, through the AI that is good at producing realistic things and say, how realistic does this look? And if it looks realistic, if it looks like something that was created from normal traffic conditions, then you don't flag it as anomalous. But if it looks atypical because traffic jams are emerging for no good reason, then that might be a sign that there's something going on. Now, pinpointing the actual vehicle is another challenge. Okay, so I'm almost out of time here. Let me sort of summarize with a couple of key takeaway points. So vehicle automation takes many forms, but in all the forms, CAVs just have more computation. And then whenever you have more computation going on, more code, that's more opportunities for compromise. And the important thing is, when we think about this from sort of the infrastructure management or the traffic flow management perspective, changing the behavior of just a small number of agents changes the flow. And so if somebody is maliciously changing the behavior of a couple of vehicles, just by maybe a software update that makes a couple of CAVs drive a little worse, you could potentially have these stealthy cyber attacks that you can't actually detect by looking at individual vehicles, but have really, really bad sort of spillback effects on congestion. Okay, so what are the action items that we identified in the future of mobility piece? We need to recognize this, and we need to recognize that CAVs pose they're important technology that have the potential to really improve things, but they also have the potential for compromise. And so I think the first step is to recognize this. The second step is to make sure that there's robust security measures that are placed on vehicles, and manufacturers are already working towards this. But this is going to be sort of a continuous game of cat and mouse as hackers find new ways to compromise these vehicles. Manufacturers are going to have to find new ways to safeguard against these attacks. And I think there's also a role for research here. There's need specifically for research to identify at the traffic level, sort of how do we identify when something is compromised, and how do we pinpoint this? And then what's the playbook for knowing that if you're a regional transportation management center, what's the playbook for knowing that you're operating with some number of vehicles that are compromised in your traffic stream? Thank you very much for your attention today. The QR code there, that's a direct link to the write-up that I wrote. I think John already posted it into the chat, so thank you very much. I don't know if there's any quick clarifying questions now, but otherwise I think there's plenty of time for questions during the round robin session at the end. And Raj, welcome back. I think you're back online. Thank you.
Thank you, Professor Stern. Yes, if there are any clarifying questions, we can take those now. Otherwise, we're going to ask Raj to pick up where he left off. Don't see anything.
I'm going to stop share here and hand it back over to you, Raj.
Please go ahead, Professor Rajamani.
Okay, so sorry about that. Too many problems today, but hopefully it works okay now.
Looks good. Not in presentation mode yet, but
Okay.
there we go.
Okay, so I think I was on this slide when I cut out, but I was going to trying to show you this video of the MnCAV vehicle with some of the modified software that we've implemented on it to enable it to work under stop and go traffic, under heavy traffic. So let me play this video here. So the set speed is the speed at which we want the car to go. The actual speed is the lower speed at which it is going because of significant traffic. So it's forced to follow other vehicles, and so it's not able to go at the desired speed. And so you can see here all the other cars on the road. And as the traffic gets heavier, the speed drops on the car. So, and then it can come to a complete stop, essentially. So this is the system operating with both the automatic steering control and adaptive cruise control. And basically it can do stop and go operation. So this is one of the things that we implemented on the MnCAV vehicle. One other aspect that we are working on right now is to fix some problems with the steering controller, especially there are some offset errors while going on sharp curves. And so we are trying to fix that and to make it follow curved roads better. So then let me move on to winter operation problems. So as I told you before, we use a Mobileye commercial system that measures distances to lane markers. What the Mobileye software does is it gives you the lateral distance to the lane markers, but it also gives you quality of line detection. So the quality of the line detection could be anywhere from 0 to 3, where 0 is very bad and 3 is very good line detection. 2 is moderate line detection. So under good road conditions, the quality of line detection is typically 3, as you can see in these plots here, the left lane line and the right lane line. So the quality is 3 most of the time. And if the quality is 3 or 2, then it is possible to engage the automatic steering control system. And so when the automatic steering control system is engaged, you get pretty good tracking of the lane center. So our accuracy in tracking the lane center is of the order of 2 centimeters. So baseline performance is pretty good. It's probably more accurate than what a human driver typically does. This slide considers a situation where there is moderate active snowfall going on. So there is active snowfall, but the lane lines are still at least partially visible. So you can see here that the left lane lines are visible, and here the the right lane lines are also partially visible. And if you look at the quality of line detection returned by Mobileye, it's 2 for quite a bit of the time. So here what happened is that we were able to engage the steering control system, but every once in a while it would drop out. So it wasn't fun to drive because the system kept getting disengaged. So this was the problem when the lane lines were quite visible and a human driver could still drive quite well, but the automatic system really could not be engaged much. This slide has some photos of conditions after a heavy snowfall in which the lane lines are mostly covered. So, so this is after snowfall has ended. The lanes themselves are quite clear, but the lane lines are covered with snow. And so here, the quality of line detection is really poor. It's quite bad most of the time. The automatic steering could not be engaged. And so even though snowfall had stopped, the lane boundaries were covered for a long time. And so this is really a problem because here the human driver can actually drive quite well. So the human driver can see where the lane is and can drive without a problem, but the automatic system cannot drive. So if lane lines are not visible, what other methods can you use to do steering control? So one possibility is to use high precision GPS. So with GPS, if you can find the absolute position of the car, and if you have a digital map, which tells you where the lane lines are in absolute coordinates, then you can use that for doing steering control. You can also have LiDAR maps. So LiDAR maps are basically where you use LiDAR to detect objects in the surrounding, like buildings, fences, trees, and so on. And that helps you localize yourself. And you can use that to find your position and do steering control. The other possibility is to do what humans do, in the sense that humans are able to drive even when the lane lines are not visible. And so if there is a control system or an advanced AI system that is able to drive even when the lane lines are not visible, that would be a good solution. So I'll just talk a little bit about the GPS solution. And I know I'm running out of time here, and then go on to my conclusion slide. So as far as GNSS or GPS, so by itself, GPS only gives you an accuracy that is of the order of 2 meters or so. So by itself, it is just not accurate enough. The position readings from it are not accurate enough to do steering control, because you need centimeter level position accuracy. But if you use RTK corrections, so if you use GPS signals and also corrections from a network of base stations with accurately known locations, then it is possible to get much more accurate positions. And so that might enable automatic steering control. And so we have the MnCOR's network, for example, and the current purpose of these stationary base stations is for land surveying. Some challenges with using this type of network for corrections is that you get a lot of obstructions in urban and suburban roads. And so you can lose the correction signals quite a bit of the time. And so if you lose the correction signals, then you again have very poor position accuracy in that case. not only that, when you lose the correction signal, it can take you a long time to reacquire the signal. And so that can really compromise automated driving. So one of the research problems that we have just started looking at is how to combine different types of sensors together at the same time to enable automatic steering control. So the objective here is to work on some novel sensor combinations that include GPS, but also some additional sensors together. And so by using a number of different sensors together, so cameras in addition to GPS and IMUs, and looking at this combination to enable more reliable automatic steering control. So with that, let me just move on to my conclusion slide. So our conclusion is basically that camera-based lane line detection systems, which are the most common systems used for steering, especially on cars sold to the general public, so those won't work when the road is covered with snow. So alternative sensing, alternative signal processing techniques are required when snow is covering the road surface. As far as the industry is concerned, so companies like Tesla, Google, Uber, and so on, they are focused on developing level 4 systems for driving in good conditions rather than L2 systems for driving in poor conditions like winter conditions. So we may not see significant improvement for many years to come unless we, meaning states like Minnesota, unless we take the initiative. These big companies are really not looking at driving in poor conditions. If the winter driving problem could be made less complex through smart infrastructure, so if, for example, the MnCOR's network is made, is improved, that could accelerate the development of more robust systems for winter driving. And then in conclusion, I also want to say that radar-based longitudinal control, that works well even in winter conditions. So from the tests that we have done, we found that radar works quite well, even under moderate active precipitation. It might fail when there is really heavy active snowfall, but it seemed to work quite well under moderate precipitation. And so as far as longitudinal control is concerned, that doesn't seem to be influenced that much by winter weather. So I'll stop with that. I hope you were all able to hear me and I was connected all the time. I just kept talking. I hope I was actually connected.
Yeah, I think that worked out. Thank you, Raj. If there are any clarifying questions, now's the time. Otherwise, Gina's going to share some updates and then we'll have a bit more time for Q&A. But I have one question. I think it falls under the clarifying questions category. And you said that with the mapping, corrected GPS, you can get to 1 centimeter accuracy. I wonder what the accuracy is without that kind of corrected, that additional information.
So the very basic GPS that we use for navigation, typically on our phones, for example, so that accuracy is of the order of 6 feet or so. So it's not very accurate.
Not enough to keep you in the lane.
No, no.
Okay, thank you, Raj. Now, Gina Baas is going to share some CAV-related, some updates on CAV-related research at the university's MnCAV ecosystem.
Great, thanks, Tony. And Raj, since he already spoke about the vehicle, I'll be able to skip through those particular slides. So just brief information overall about MnCAV ecosystem. So it was established at the University of Minnesota in 2020, and it's housed at CTS. And it's really what we're considering the umbrella program for connected and automated vehicle research, engagement, and workforce activities at the University of Minnesota. So really excited about this opportunity to really take advantage of the existing university expertise that we already have. So these are sort of the 5 major strategic initiatives for the MnCAV ecosystem. That one is to build the infrastructure to support research and development, and Raj just shared information with you about the vehicle. Second is, again, to excel in our unique areas of research strength, and Raj and Raphael are both tremendous examples of the expertise that we have available at the University of Minnesota. Third, we want to enhance and expand our partnerships with government, academia, and industry. And as you know, Thomas had mentioned and others have talked about, it's really important to bring all 3 together to address the challenges and opportunities that might be available through connected and automated vehicles. Fourth, we really want to be part of the solution in terms of building public awareness and education to help educate and inform the public on connected and automated vehicles. And then finally, again, as part of our university mission, is to develop that future workforce that is going to be able to support emerging needs in this space. So Raj talked already about the vehicle. The one thing I do want to highlight is that this was paid for through all university funding to enable the university to have this resource for research. So we're really excited about that. And we have developed processes that support the vehicle use so that it can be written into proposals by faculty, researchers, and others, so that we're able to maintain this piece of infrastructure, this vehicle. And again, these are just a couple of close-up photos of some of the sensors and the cameras that are part of this, and then a look at the hardware that is in the back of the vehicle. And we're able to collect about 23 terabytes of data at any given time. So again, some of the advantages, and Raj has talked a little bit about this, but it is a customizable platform that allows researchers to experiment on, whatever they might be interested in, and including, we also see it as a vessel or a vehicle for data collection and analysis for projects as well. Our 5 major research focus areas, although we obviously are engaged in other areas as well: equity and public perception and trust, vulnerable road users, cold weather conditions, and the connected environment. And I would say one thing that I think CTS does well as an interdisciplinary center is that we bring together the sort of 2 sides of the coin. So both the policy and planning aspects of topics as well, and bringing them together with the technology, the human factors. So that is something that we are uniquely positioned at the university to do. And right now we've got probably about a dozen active CAV-related projects, including the 2 that Raj and Raphael spoke about. And we also have 3 research projects that are associated with the 3 shuttle pilots that Thomas spoke about earlier. One of the new initiatives that I did want to talk about is a new partnership that the University of Minnesota has become involved with. And that is the Center for Connected and Automated Transportation Center, or CCAT, which is the designated US DOT Region 5 University Transportation Center. And it's headed up by the University of Michigan and by a former U of M faculty member, Henry Liu. So we're excited that we have that opportunity to kind of build on this connection with Henry. So his center was renewed at $15 million, announced in February, and the University of Minnesota is a new partner, one of 9 partners that are going to be part of the center, part of CCAT, and which will mean, up to about $500,000 per year for additional CAV-related research and other activities at the University of Minnesota. The other and another initiative that I wanted to mention was Drive Minnesota. It was a 1,086-mile trip across Minnesota this summer, whose purpose was to understand the CAV infrastructure and policy readiness, as well as to engage with politicians and transportation professionals to talk to them about the state of CAV in Minnesota, as well as nationally, and to also talk a little bit about some of the things that were discovered or preliminary findings from the drive. So if you look to the right, you can see the route that was taken over the course of 4 days. And during those 4 days, the team stopped in 8 different cities to talk about the data that was being observed and the data collection, but also to, like I said, to engage stakeholders on these topics. The project, I'm not going to go into detail. I will say that the team is going to be doing a session at Minnesota's Transportation Conference in May. So if you want the details, please plan to attend that session during Minnesota's Transportation Conference, where there will be more information shared. The project was completed in January, and CTS had a recent Catalyst article about the drive, and you'll be able to access the report on an ongoing basis from the MnDOT CAV website, and we're just waiting for that to be posted. So I'm not going to go into any detail about the findings, but just again to highlight this was a project where it again combined the sort of the research and the data piece with engagement and policy. And then the final thing I wanted to mention is the CAV Career Pathways Camp that CTS started back in 2021, and we're scheduled to have our 3rd camp this summer again in August. It's funded through a program that Federal Highway Administration offers and is administered by the MnDOT Office of Civil Rights, and they are tremendous partners with us on this effort. So it's a 1-week summer camp that we offer for up to 20 high school students, then in the grades 10 through 12. And it's an opportunity to hopefully introduce students to CAV technologies and to CAV career and educational opportunities. And so at this point, I want to put in a plug that we are always looking for volunteers to help us plan and lead sessions during the camp. So if anybody is interested in volunteering, please reach out to me, because we would love to have your participation. And so with that, I'm going to end and just really conclude by saying we have a lot of really interesting and exciting work going on in this space at the university, and look forward to sharing more about it in the months and years to come. So thanks, and I'll turn it back to Tony.
Thanks, Gina. Yeah, that came across very clear that there's a lot going on and a lot of exciting work going on at the university. So thank you, Gina. Thank you, Raj. Thank you, Raphael. A round of applause for our speakers today. And we do have a little bit of time for Q&A, and I'm going to pass the baton to Joe for that.
All right. Thank you, Tony. Thank you, everyone. Just a quick reminder to use the raise hand feature to ask questions verbally, if that's how you prefer to do so, or type your questions and comments using the Q&A feature. I will read the questions and comments out loud, and then the speaker will respond. So I have one question already in the Q&A that says, understanding, I think this is probably for all 3 speakers, understanding that the bigger companies are designing without Minnesota use cases in mind, is there any estimate of how much it would cost to retrofit our whole roadway system to actually achieve the stated benefits for automated vehicles?
Should I try to take that? So as far as the GPS correction system that I talked about, there's 2 types of technologies: the RTK and then the PPP systems for offering corrections. And I personally feel that it's not going to be very expensive. I think by using a hybrid combination of the RTK and the PPP systems, I think it's possible to really provide coverage for all portions of Minnesota, and it will not be very expensive to do that But I don't really have a number in terms of how much it would actually cost.
All right, Dr. Stern or Thomas, if you have anything to add to that.
Yeah, I mean, I guess I'll quickly go because I think the answer is I'm not sure. I mean, I think Professor Rajamani sort of summed it up really good. There's just a lot, and I think a lot of the stuff that Professor Rajamani was talking about with in terms of like it's not just the infrastructure costs, but it's also the associated winter maintenance costs. If you're going to rely on the camera-based systems and not have the high accuracy, RTK corrected GPS. So I think Professor Rajamani summed it up well. I don't know, Thomas, if you had something to add to that.
Yeah, no, I think you've all summed it up well. I think the only thing I'll add is we are trying to do the testing in Minnesota winter weathers to better understand that. So I think that's a big reason why we're doing some of those pilot projects to understand what it takes to operate this technology in our harsh Minnesota winters that we have.
Yeah, I think that's an excellent point. There is this sort of the need to actually try it and see what happens. Because as someone who's done some experimental work before, and as people who've probably done things in the field before, things never quite end up the way you expect them to. And so there's going to be unexpected challenges. There's the challenges that are kind of that we see right now, but there's also going to be unexpected challenges that come up, especially in this winter weather environment. I know so a lot of people talk about sort of the connection between electrification and automation, because those are sort of often seen as possibly going hand in hand when we think about how our environment changes or how our transportation landscape changes. And there's going to be a bunch of challenges there as well for winter operating in both the extreme colds and the high temperatures that we see in Minnesota.
I might add that
was
we
gonna say,
do use high accuracy GNS for driver assistance for snowplow operators, but we primarily are in rural areas. There clearly are issues operating in an urban environment where you have multipath issues related to buildings that surround you. So we have mostly focused on the rural world, and I think there's lots of potential for additional research, such as Raj has mentioned, to combine multiple sensors to take care of the whole, so to speak, that exist in having a corrected high accuracy position for the vehicle.
All right, thank you all. I have one other question in here that I see. How can Midwest-based NPOs work/partner/collaborate with the university consortia on program policy development, et cetera?
Well, yeah, thank you for that question. And David, I think you had asked earlier about collaboration with Wisconsin DOT. The University of Wisconsin-Madison and David Noyce, who's a professor at University of Wisconsin, is one of the members of of the consortia that is part of CCAT. Raj and Raphael both will have initial projects starting once we get our funding and we get everything in place with our agreement with Michigan. So I would say, reach out to me, or if your interest is in one of Raj or Raphael's areas, feel free to reach out to any of us, and we can certainly connect with our partners, our collaborators, and try to identify where there might be some of those opportunities. So I think that the first step is just reach out and let us know what your thoughts or ideas are, and we can look at ways to address them in the future.
Well, we are at time, so I want to thank our speakers again, and thank you to all our participants for coming. Just a note, we are always interested in ideas for these webinars, and we're always interested in what kinds of issues your agency might be facing. Feel free to reach out to Gina, Joe, or myself on those topics. Thank you, everyone.
Thank you. Bye.
Bye.